Hello, cosmic explorers, and welcome to Cosmic Facts. Buckle up, because today we're diving headfirst into one of the wildest, most mind-bending plot twists in the history of science: Albert Einstein's theory of relativity. Why does time slow down when you're zooming through space? How can space itself bend like a cosmic yoga mat? And what made the entire scientific world drop their jaws in the 20th century? Let's embark on this epic journey to find out. Before we get to Einstein's revolutionary ideas, let's set the stage with the world he disrupted. Picture the late 1600s. Isaac Newton, the guy with the apple and the gravity obsession, ruled the scientific scene. Newton said space and time were like a giant, unchanging stage. Planets, apples, and people all moved on this stage, and time ticked along at the same pace everywhere, no exceptions. Imagine you're on a train moving at 20 meters per second, and you toss an apple forward at 10 meters per second. Someone standing on the ground would see that apple zipping along at 30 meters per second. It's just basic addition, right? Newton's rules were so intuitive that they powered everything from building bridges to predicting planetary orbits. But by the 1800s, cracks started appearing in Newton's perfect world. Scientists like James Clerk Maxwell were studying light and electromagnetism, and they discovered something bizarre. Light always travels at a constant speed of 300,000 kilometers per second, 186,000 miles per second if you're feeling imperial, whether you're standing still, running, or riding a rocket. This didn't fit Newton's neat little system. To explain it, scientists invented the idea of the ether, a mysterious substance they thought filled space and carried light waves. But in 1887, the Michelson-Morley experiment dropped a bombshell. There was no ether. Light didn't need a medium to travel, and its speed was the same no matter how you measured it. The scientific community was shook. Newton's stage was starting to wobble. Enter another key player, Hendrik Lorentz, a Dutch physicist who proposed that objects moving near the speed of light might shrink, and time might slow down to keep light's speed constant. These ideas, called the Lorentz transformations, were like a teaser trailer for what was coming next. The stage was set for a young genius to rewrite the rules of the universe. In 1905, a 26-year-old patent clerk in Switzerland named Albert Einstein, yep, not even a professor, just a guy crunching paperwork, published the theory of special relativity, and it was a game changer. Einstein said, forget Newton's fixed stage. Space and time are not absolute. They're relative, stretching and squishing depending on how fast you're moving. Let's break this down with a fun scenario. You and your bestie are on a spaceship blasting through the cosmos at 90% the speed of light. You're sipping cosmic coffee, and you check your watch. 1 minute passes. But your other friend, chilling back on Earth, peeks at your spaceship's clock through a super telescope. To them, your clock is crawling, taking way longer than a minute to tick by. This is called time dilation, and it's not a glitch, it's how the universe works. Why? Because the speed of light is the ultimate speed limit, and space and time have to bend to keep it constant. Here's another analogy. Think of the universe as a strict traffic cop. No matter how fast you're driving, whether you're on a bicycle or a hyperspeed spaceship, light always cruises at 300,000 kilometers per second relative to you. To enforce this rule, time slows down and space warps when you try to catch up. But wait, there's more. Einstein also said that if you're moving crazy fast, you'd physically shrink in the direction of motion. Not like you're hitting the gym, but your spaceship and even your body would get squished shorter. This is length contraction, and it's another way the universe keeps light's speed untouchable. Let's make it real. Imagine you're racing through space in a 100-meter-long spaceship. To someone on Earth, your ship might look like it's only 50 meters long at near light speeds. Don't worry, you wouldn't feel the squeeze. It's all relative. And then comes the equation that changed everything: E equals mc squared. This tiny formula is like the ultimate cheat code for the universe. It says energy E and mass m are interchangeable, connected by the speed of light squared, see superscript 2. A small amount of mass can unleash a colossal amount of energy. This is why nuclear reactors and bombs are so powerful. A little bit of uranium or hydrogen can light up a city or, sadly, destroy one. To put it in perspective, if you could convert the mass of a single paperclip into energy, it could power your house for months. But Einstein wasn't done shaking things up. In 1915, he dropped the theory of general relativity, and this one was an even bigger mind-blower. He said gravity isn't just a force pulling things together, like Newton thought. It's the bending of space-time caused by massive objects. Picture space-time as a stretchy trampoline. Drop a heavy bowling ball, like the sun, on it, and it creates a deep dent. Now roll a marble, like Earth, across the trampoline. It'll curve around the dent, orbiting the bowling ball. That's how gravity works. Planets and stars warp the fabric of space-time, and everything follows those curves. Einstein made a bold prediction. If space-time can bend, then light should bend too when it passes near a massive object. In 1919, during a solar eclipse, British astronomer Arthur Eddington tested this idea. He measured the position of stars near the Sun and found that their light was indeed bent by the Sun's gravity, exactly as Einstein predicted. The news hit the headlines, and Einstein went from patent clerk to global superstar overnight. But let's not sugarcoat it. Einstein's ideas weren't an instant hit. When he first published special relativity, many scientists thought he was out of his mind. Time slowing down? Space shrinking? It sounded like something out of a sci-fi novel, not serious physics. Some physicists, like Max Abraham, argued that Einstein's math was too abstract and unprovable. Others, loyal to Newton, worried that relativity would throw out centuries of established science. Even Lorentz, whose work inspired Einstein, was initially skeptical about the physical reality of time dilation. The math was airtight, but it took years of experiments to win over the skeptics. The 1919 eclipse observation was a turning point, but other tests, like the precession of Mercury's orbit, also confirmed general relativity. Mercury's orbit didn't quite match Newton's predictions, but Einstein's equations nailed it, proving that space-time curvature was real. Over time, the doubters had to admit, Einstein was onto something big. So, how does the theory of relativity affect you? It's not just for brainy physicists. It's in your everyday life. Let's talk GPS. Those satellites orbiting Earth are in a weaker gravitational field than your phone on the ground, so their clocks tick slightly faster due to general relativity. Plus, they're moving fast, so special relativity slows their clocks a bit. Without correcting for both effects, GPS would drift by kilometers, and you'd end up in the wrong neighborhood. Then there's black holes. General relativity predicted these cosmic monsters, where space-time is so warped that nothing, not even light, can escape. In 2019, the Event Horizon Telescope captured the first image of a black hole's shadow, a glowing ring of gas around a dark void, straight out of Einstein's playbook. Relativity also shapes our understanding of the universe's history. It underpins the Big Bang Theory, explaining how the universe expanded from a single point 13.8 billion years ago. It predicts gravitational waves, ripples in space-time caused by massive objects like colliding black holes. In 2015, the LIGO experiment detected these waves, giving us another high five for Einstein. And let's not forget cosmology's wild side. Relativity hints at possibilities like time travel and wormholes, though they're still theoretical. Speaking of wormholes, let's geek out about science fiction for a minute. The theory of relativity is the secret sauce behind so many sci-fi blockbusters. Ever seen Interstellar? That movie's heart-pounding scenes of time dilation, where years pass on Earth while minutes tick by near a black hole, are straight from special relativity. Or how about Star Trek's warp drives and wormholes? Those are inspired by general relativity's idea that space-time can be warped to connect distant points. Wormholes are hypothetical tunnels through space-time that could, in theory, let you jump from one side of the galaxy to the other faster than light. We haven't found any wormholes yet, but relativity says they're mathematically possible, which is enough to keep sci-fi fans dreaming. Even the concept of time travel, like in Back to the Future, owes a nod to Einstein. While we can hop in a DeLorean and visit the 1980s, relativity allows for forward time travel through time dilation. If you zipped around near light speed for a few years, you could return to Earth to find decades had passed. Kind of like a one-way ticket to the future. Relativity doesn't just fuel Hollywood. It's also sparked debates in physics. For example, it doesn't play nicely with quantum mechanics, the other pillar of modern physics. Quantum mechanics governs the tiny world of atoms and particles, while relativity rules the massive scale of stars and galaxies. Scientists are still trying to unify these two theories into a theory of everything, and relativity is at the heart of that quest. Think of it as the ultimate cosmic puzzle. Now, let's tackle some questions you might have, Cosmic Facts style. First up, does time dilation mean I can stay young forever? Well, sort of. If you lived on a super-fast spaceship, you'd age slower than people on Earth. But you'd still feel time passing normally. It's just that Earth clocks would race ahead. Next, can we really bend space? Yep. Massive objects like the sun and black holes do it all the time, and we've measured it. Finally, is E equals mc squared why my diet isn't working? Haha, no, but it does mean your morning coffee has a tiny bit of mass energy you could theoretically tap into. Just don't try it at home. So, there you have it. The theory of relativity isn't just a theory, it's a cosmic revolution that flipped 20th century science on its head. It showed us that the universe is a weirder, wilder place than we ever imagined, with stretchy space, squishy time, and mind-boggling possibilities. Einstein didn't just change physics. He changed how we see our place in the cosmos, from the GPS in your pocket to the black holes in deep space. What blew your mind the most? Was it time dilation, bending light, or maybe the sci-fi vibes of wormholes? Drop your thoughts in the comments, and tell us your favorite sci-fi movie or book inspired by relativity, Interstellar, Star Wars, or something else? Hit that like button to show Cosmic Facts some love. And if you want more cosmic brainbusters, smash that subscribe button and ring the bell so you never miss a video. Got a topic you're dying to explore? Maybe quantum mechanics, dark matter, or the search for alien life? Let us know below, and we'll dive into it next time. Thanks for joining us on this wild ride through the universe. See you in the next one.